This is Jeff Coles. In this unit, we're going to be looking at the solution of a couple sets of linear systems, the analytical solutions, and then seeing how the nature of the solution can be characterized simply by looking at the eigenvalues. So in previous work, we looked at the linear autonomous differential equation that looked like this: y primed equals ky, where that is that the rate of change of y with respect to time was proportional to the amount of y at any time. And this was a model for growth or decay, money, and biology. And we saw the solution to that. The general solution was that y of t equals c, an arbitrary constant, e to the kt. Was an exponential function, satisfied that, and that came from that important property, the exponential function, that the derivative with respect to time of e to the t is equal to e to the t. It's a special function. It has this property, and therefore the derivative with respect to time of e to the kt equals ke to the kt. Can you find that out using the chain rule? Now we're considering systems of linear equations. So a system could be written as follows. The rate of change of x with respect to time equals ax plus by, and y primed equals cx plus dy. This is the most generic form of a coupled set of two differential equations. We can simplify this if we define the state vector z equals xy, and therefore z prime, the rate of change of z with respect to time, is the derivative of the two components, x prime, y prime. We can write the system above as z primed equals the matrix A times z, where A is equal to A, B, C, D, from this up here. So it's a compact form of writing that, and thus we can have a system of 15 linear equations and write it using the simple compact notation. Now, when we examine this equation up here, we found that this was a valid solution to that system. So what about guessing a solution similar to that to satisfy this system of differential equations? We're looking for a solution z of t, which in our two equation system represents x of t, y of t. That's what we're looking for. So we're going to guess something similar. Let's say z equals v, some vector, e to the lambda t. Lambda is yet to be determined, and v is a vector yet to be determined. E to the lambda t is just a scalar. In order to have the dimensions the same on both sides, basically a column vector of size 2, z and v both we need this vector v. So we'll just let v have two components, alpha and beta. So it's a 2-row vector. It's a 2-by-1 vector. And now what we'll do is we'll take the derivative and see if we can get this to satisfy the original differential equation. So we're guessing a solution. The important thing is, does it satisfy the differential equation? So we say z prime. We take the derivative. So again, so z, if we write it in longhand, is equal to x and y of t, and which are equal to alpha e to the lambda t and beta e to the lambda t. We'll take the derivative of that, and we get equals alpha lambda e to the lambda t. Remember, the lambda comes out when we take the derivative. Pen is not writing here. And beta lambda e to the lambda t. which we can write as, considering alpha and beta are this vector v, we can write this as equal to lambda e to the lambda t times this vector v. Now, again, the differential equation is z primed equals a z. Is this true? Well, here's z primed. So we guessed z equals v e to the lambda t. We took the derivative of that and we found that z primed equals lambda e to the lambda t times v. Now we're going to take these and plug them and see if it satisfies this. So we have lambda e to the lambda t times v equals a times our guess z, v e to the lambda t. Now we can simplify this. We'll get rid of these guys. These terms are the same on both sides. And we have lambda, a scalar times this vector v, is equal to this matrix A, which comes from our original differential set of differential equations, times v. I'm just going to flip-flop the left and right side, and you should recognize this as the original eigenproblem. This is what defined our eigenproblem. You had the eigenproblem was a set of vectors v and scalars lambda, which satisfied this relationship. Essentially, it's a magical vector v such that you multiply your matrix A times that vector, and all it does is stretch it. It stretches it by an amount lambda. It doesn't rotate it at all. So in this case, the v's that satisfied this relation were the eigenvectors, and the lambdas were the eigenvalues. So this tells me that, yes, you can satisfy this differential equation here, which represents the shorthand of our original, sorry about this, coupled set of linear equations, right? We can write it in this form, z primed equals az, where z is a vector and a is a matrix. We guess the solution z equals ve to the lambda t, and then we check it, and we find, yes, it satisfies that provided the v in our guess, let me write our general solution again, z of t equals v e to the lambda t. This satisfies our original set of linear differential equations provided v is an eigenvector of A and lambda is an eigenvalue of A. Now remember that we have multiple eigenvalues and eigenvectors. A 2x2 matrix will have in general two eigenvectors, or I'll say two eigenvalues. Associated with each of those eigenvalues is a particular eigenvector. So in this case we'll have a general solution z of t equals c1 e to the lambda 1t times the first eigenvector plus c2 e to the second eigenvalue times t times the eigenvector associated with that eigenvalue. Just like in the case of a single linear equation, we have this arbitrary constant which we can add in there, and it will still satisfy the original differential equation. So this is a general solution if it were a 2x2 matrix. For a 3x3 we'd have an additional term. If it's an n by n matrix we'd have up to n terms of this form. And so in this case we're focusing on 2x2. So this still represents two equations because we have these vectors v here, right? Which may have different components in them. So we're going to go ahead and solve one example. So we'll start with just an example. So we have x prime equals negative 4x plus y. This is in your lecture notes. And we have y prime equals 2x minus 3y. This is, this is a set of linear equations. You see here our original we called a is minus 4 and b is 1 and c is 2 and d is minus 3. So we can write it as we've been writing it. In matrix form we write it like this. xy prime equals minus 4, 1, 2 minus 3 times xy That's the equivalent of writing it as z primed equals a z. Now remember, it's the eigenvectors and eigenvalues of a that get plugged into our general solution. So we go ahead and solve for the eigenvalues. Remember the eigenvalue problem, you just say the determinant of a minus lambda I, I is the identity matrix, equals 0. And we solve for those lambdas from the characteristic equation. In this case, it's a quadratic equation with two roots, lambda 1 and lambda 2, that look like this. Lambda 1 comma lambda 2 equals minus 2 minus 5. Nice simple integer numbers. Both of these are real. And both are negative. Now the eigenvector associated with lambda 1, which we can solve for, but we'll just say MATLAB solved it for us. The eigenvector is 1, 2. And for lambda 2, the eigenvector is 1 minus 1. Now what we're going to do is plug this into our general equation. Remember, our general equation looked like this. Z of t equals C1 e to the negative, e to the lambda 1, lambda 1 t times V1 plus C2 e to the lambda 2t times V2. Right, so I'm going to have actual numbers now, so let's plug it in. So we have equals C1 e to the negative 2t, that's the first eigenvalue, times the first eigenvector, plus C2 e to the negative 5t, that's supposed to be a 5, let me make that a little clearer, e to the negative 5t times 1 minus 1. Good. Now we can see that this is actually represents two equations, two solutions. We'll just write it out in longhand. X of t, the first one looks like this. C1 e to the negative 2t times that first component of the eigenvector 1 plus C2 e to the negative 5t times the first component of the eigenvector also happens to be 1. And our y of t is going to be 2, here's the 2, times C1 e to the negative 2t minus 1 times C2 e to the negative 5t. So there's your general solution, written in shorthand, written in longhand, of this system, original system of differential equations. Now we have these arbitrary constants. How do we satisfy them? Well, we need additional conditions. Typically these are initial conditions. Let's just make some up. We'll let x at t equals 0 equals 0. We'll let y at t equals 0 equal 3. Now we come back to our equations up here. Here's x. So x at t equals 0 is equal to what? It's C1 times e to the 0. E to the 0 is 1, plus C2 times e to the 0. E to the 0 is 1. So we have x at t equals 0 equals C1 plus C2. Now we have y. Y at t equals 0 is going to be similar. Remember, e to the 0, or e times 0 is 1. So this is going to be equal to 3, that was what we set it equal to, equals 2c1 minus c2. So we have two equations for two unknowns, for c1 and c2, and we can solve for them. And we get for the first one, we get c1 equals negative c2, and you plug it in here, and solve for c1, and we get c1 equals 1, and c2 equals minus 1. Okay? Now we'll go back to our general solution here, and we have actual numbers for the constants because we set some initial conditions. We'll plug those in, and we will get a particular solution for x and y. X of t equals e to the negative 2t minus e to the negative 5t. We get y of t equals 2e to the negative 2t plus e to the negative 5t. This is a set of particular solutions for x of t and y of t that will satisfy our original differential equations and our initial conditions C1 and C2. Let's just look at them now, this nature of the solution. What happens as t goes to infinity? Well, e to the minus anything, or minus 2t or minus 5t, both of those will go to 0. E to the negative large number is 0. So you see all four terms here are going to disappear as t goes to infinity. And we can quickly see this satisfy the initial conditions. If we, at t equals 0, x of t is 1 minus 1, which is 0. That's correct. And at t equals 0, y of t equals 2 plus 1, which is 3, which is correct. So it satisfies the initial condition. We can see that all terms disappear as time goes to infinity, and that is because the exponents all are negative. They all are negative because the eigenvalues were negative. So the eigenvalues are controlling this. So this 2 here and this minus 1 here, those came from both the initial conditions and the original eigenvectors. But what they're multiplying, but the time dependency is in the exponential, and it's controlled by the eigenvalue. Here it is a negative real eigenvalue. All these terms will decay and disappear. We can look at it as a function of time. Remember, x at time t equals 0 is 0. Y at time t equals 0 is 3. And the solution looks something like this. X comes up because it's positively associated with y, which exists initially. And then the decay term kicks in and kills it. And y just simply decays, something like this. So here's y of t, x of t. So there's some kind of transient here, right? There's some kind of activity in the transient, but the long-term solution looks something like this. It will asymptote to 0. The long-term solution is decay. We can also look at it from the perspective of phase space, where we plot x versus y, x, y. Oops. Now we start off at x equals 0, y equals 3. There's the initial condition of the system. We first gain some x. Y is already decreasing initially. And then x starts to die out, and everything goes towards 0, 0, which is the final solution of this problem. Now note at this point that for any system of linear equations, again, that look like this, x prime equals ax plus by, and y primed equals cx plus dy. Again, this is a generic set of linear coupled equations. These are, there's only one critical point. There's one critical point to a linear set of equations, and that is at x equals 0 and y equals 0. Now we come up to examine this phase space in particular. The system moves like this, towards 0, 0. And if we were to perturb it back out here again, it would extend towards 0, 0. This critical point is stable. For this system, it is stable. We can plot the entire phase space, including negative numbers. Here's the one critical point at the origin. Again, we started here and we ended up there. We will find, no matter where you are, the solution is attracted as more or less directly with some, some slight deviation, but essentially towards the critical point. It is a stable critical point, and it has a name. The name of this critical point is a nodal sink. It's a sink. You can think about it when you drain the sink and all the water goes down into the hole. A sink is sucking in the solution towards our critical point right here. And it's a nodal sink because essentially the solution migrates directly to it. There's no behavior in the time domain. There's no oscillatory behavior in the time domain. It just simply decays into the solution. We'll see later that oscillatory behavior requires that the eigenvalues be complex, meaning they have a non-zero imaginary component. So just to review, we took our generic linear set of coupled equations. Maybe I'll just go through the slides. You can hold on to your brain for a second. Apologize about this. So we took, that was from earlier. We took our linear set of equations that look something like this. We wrote it as in matrix vector form. It looked like this. We guessed a solution of this form, which is analogous to guessing c e to the lambda t for a single equation. Here we have v. We need a vector to make sure this is a two-dimensional solution, in this case with two equations. We determined the derivative of that, and then we checked it. Here's our original differential equation. Here's our guess. Here's the derivative of our guess. We plug it into the differential equation. It satisfies it under the conditions that v, this vector v that we put in our guess solution, is an eigenvector, and lambda, the scalar we put in our guess solution, is the associated eigenvalue. Now we have multiple ones for our 2D system, so we have to write our generic solution in this form here. And then what we did was we worked out an actual problem. We had real numbers. This is our matrix A. The eigenvalues of that matrix are -2 and -5, and here are the associated eigenvectors. That allowed us to write this generic solution here, general solution here. We have these constants that we need to define using initial conditions, which is what we did next. We plugged in some initial conditions. We let x at t equals 0 equals 0 and y at t equals 0 equal 3, allowing us to solve for C1 and C2 as a system of two equations and two unknowns. And then we had this particular solution, and we looked in more detail at the particular solution. The key thing is, because we had the negative real eigenvalues, happening to be -2 and -5, these negative terms mean that all these terms go to 0 eventually, as just exponential decay. And that's what we see in both the time series and the phase plane, and if we consider a more general phase space, x versus y, including negative values, everything's attracted towards our one critical point of our linear system, which exists at the origin. Now, contrary to that, we'll consider one other, and then we'll consider the rest in a follow-up lecture. If our eigenvalues, our lambdas, from our matrix happen to be real and positive, such that we have lambda 1 greater than 0, lambda 2 greater than 0, we would have ended up with a solution that looked like this. X of t equals some constant, e to the lambda 1 of t greater than 0, plus k2 e to the lambda 2 of t greater than 0, and our y of t will look the same with different constants up front. Again, the constants come from both the eigenvectors and the initial conditions. What's affecting the time dependency is only the eigenvalues. Lambda 3t plus k4 e to the lambda, excuse me, it's no lambda 3, this is lambda 1, lambda 2t. Now, if they were both real and both positive, all these exponential terms are going to grow with time. And that means the solution is going to go away from the origin. Generally speaking, if we plot phase space, including negative values, x and y, we have our one critical point here. That tells us that the solution, if perturbed away from this critical point, is going to grow away from the critical point as these exponentials kick in. This type of solution is known as a nodal source, as opposed to the previous one, which is a nodal sink. And it is, as you may have guessed, unstable. Any perturbation from the critical point will take it away from the critical point. Let's end the lecture there, and we'll look at the remaining types, characterizations of the critical point of linear systems in the next unit.